At this very moment, the fastest object ever constructed by human hands is racing through space at 430,000 miles per hour. At such an extraordinary velocity, you could travel completely around our planet in less than 4 minutes. And yet, this same spacecraft, moving at a speed that would instantly vaporize you if you collided with anything solid, would still need more than 6,000 years to reach the closest star to our Sun. Here is something that will change everything you thought you understood about traveling through space. The distance a human being could actually traverse during a single lifetime is not constrained by our engineering capabilities, or by funding, or by human determination. It is constrained by a fundamental barrier woven directly into the fabric of reality itself. Even with this limitation, there exists a loophole so extraordinary that it could allow you to reach locations millions of light years distant while experiencing only decades of aging. If you want to discover precisely how far a single human lifetime can extend across the cosmos, and if you enjoy this kind of content, please consider liking and subscribing. It genuinely helps more than you might realize. The fastest object humanity has ever created is currently traveling through the void at a velocity that challenges ordinary understanding. The Parker Solar Probe, launched in 2018, has reached speeds exceeding 430,000 miles per hour during its closest approaches to our star. At this velocity, the probe moves quickly enough to traverse the entire continental United States in less than 25 seconds. It travels so rapidly that if you were standing in New York and blinked twice, the spacecraft would have already passed Los Angeles, continued across the Pacific Ocean, and be nearing Hawaii. This achievement represents the absolute peak of human engineering capability. Decades of technological advancement, billions of dollars in resources, and the combined knowledge of thousands of scientists and engineers all contributed to this success. The Parker Solar Probe uses a series of gravitational assists from Venus to reach velocities no chemical rocket could ever achieve by itself. Each close pass steals a small amount of the planet's orbital energy, gradually building velocity over years of precise trajectory planning. The probe represents humanity's greatest single accomplishment in achieving high velocity through the cosmic void. To truly appreciate how remarkable this speed is, consider that for most of human history, the fastest we could travel was about 25 miles per hour. By 1969, Apollo astronauts reached nearly 25,000 miles per hour, the fastest any human being has ever traveled. The Parker Solar Probe moves 17,000 times faster than those Apollo astronauts. It travels at a velocity so extreme that no human could survive aboard it. Not because of the speed itself, but because the trajectory passes close enough to the Sun to experience temperatures exceeding 2,500 degrees Fahrenheit. This is velocity achieved through decades of gravitational choreography, not through raw engine power. Yet even this extraordinary speed reveals a crushing truth about our cosmic limitations. At 430,000 miles per hour, the Parker Solar Probe would require approximately 6,600 years to reach Proxima Centauri, our nearest neighboring star, located just 4.24 light-years away. To put this in human terms, a journey that began when the ancient Sumerians first invented writing would only now be approaching its destination. A human lifetime spans roughly 80 years. This means that traveling at humanity's current maximum velocity, you could cover barely more than 1% of the distance to the nearest star before your heart beat its final time. The mathematics become even more sobering when you consider what one human lifetime actually accomplishes at these record-breaking speeds. Traveling continuously at the Parker Solar Probe's peak velocity for 80 years would carry you approximately 3 trillion miles. Written out completely, that number contains 12 zeros. It sounds unimaginably vast until you measure it against the true scale of cosmic distances. 3 trillion miles equals roughly 0.05 light-years. The nearest star system sits more than 80 times farther away than what an entire human lifetime at maximum velocity could cover. You would spend your entire existence traveling and never come close to leaving our stellar neighborhood. The Oort cloud provides another sobering reference point. This frozen spherical shell of ancient comets marks the outermost boundary of our sun's gravitational influence. It extends up to 100,000 astronomical units from the sun, with 1 astronomical unit being the distance from Earth to the sun, roughly 93 million miles. The Oort cloud represents the true edge of our solar system, the point where the sun's gravity finally loses its grip and interstellar space truly begins. At humanity's current maximum speed, reaching even the inner edge of the Oort cloud would require approximately 600 years of continuous travel. An entire human lifetime at unprecedented velocities would not even escape our solar system's sphere of gravitational dominance. We would die long before leaving the sun's extended family of orbiting debris. Our entire existence of travel would accomplish less than crossing from Manhattan to Brooklyn when measured against the true scale of even our local cosmic neighborhood. Consider the Voyager 1 spacecraft for perspective on what decades of actual space travel accomplish. This remarkable probe has traveled farther from Earth than any other human-made object in history. After more than 47 years of continuous journey through interplanetary and now interstellar space, Voyager 1 has covered approximately 15 billion miles. This distance took nearly half a century to achieve, and the probe continues adding to its record every second of every day. Voyager 1 crossed the heliopause in 2012, officially entering interstellar space. This boundary marks where the sun's solar wind loses its battle against the pressure of the interstellar medium, the thin gas and dust that fills the space between stars. Headlines proclaimed that Voyager had left the solar system, technically true in one sense, but deeply misleading in another. The probe escaped the sun's magnetic influence, but remains firmly within the sun's gravitational domain. It will not pass beyond the Oort cloud for another 30,000 years. 15 billion miles sounds impressive until you realize it represents less than 0.03% of the distance to the nearest star. Voyager 1 travels at approximately 38,000 miles per hour relative to the Sun. This velocity, while extraordinary by earthly standards, reveals the vast gulf between human achievement and cosmic requirement. At this speed, the probe would need over 70,000 years to reach Proxima Centauri. When Voyager 1 finally arrives at the distance of the nearest star, assuming it survives the journey through interstellar space, the humans who launched it will have been extinct longer than our entire species has currently existed. Homo sapiens have walked Earth for roughly 300,000 years. Voyager 1 needs more than twice that span to reach even the closest stellar system. This comparison reveals something deeply unsettling about the scale of cosmic distances. Space is large in a way that makes human timescales completely irrelevant. The universe is not built on a human scale. The distances between stars reflect the random distribution of matter after the Big Bang, not some cosmic consideration for the convenience of future space travelers. The gulf between our current capabilities and the requirements for meaningful interstellar exploration represents not merely a technological gap to be bridged, but a fundamental mismatch between human biology and cosmic geography. Chemical rockets face fundamental limitations imposed by physics. The tyranny of the rocket equation means that reaching even modest fractions of light speed using chemical propulsion would require fuel masses larger than all the matter in the observable universe. Chemical rockets represent dead-end technology for interstellar travel. Nuclear propulsion offers potential improvements. Nuclear reactions release millions of times more energy per unit mass than chemical reactions. A nuclear rocket could theoretically achieve exhaust velocities orders of magnitude higher than the best chemical engines, dramatically reducing the fuel mass required for a given final velocity. Various nuclear propulsion concepts have been proposed over the decades. Nuclear thermal rockets heat propellant using a nuclear reactor, achieving exhaust velocities several times higher than chemical rockets. Nuclear pulse propulsion, the idea of detonating nuclear bombs behind a spacecraft and riding the shockwave, could potentially reach even higher velocities. Project Orion, designed in the 1950s, proposed using this technique to reach a few percent of light speed. Antimatter represents the theoretical ultimate in energy density. When matter and antimatter collide, they annihilate completely, converting 100% of their combined mass directly into energy, according to Einstein's famous equation. No other energy source achieves such perfect conversion efficiency. A spacecraft powered by matter-antimatter annihilation could theoretically accelerate to significant fractions of light speed without requiring impossibly large fuel masses. But antimatter faces severe practical challenges. Currently, humanity can produce only infinitesimal amounts of antimatter at enormous cost. CERN's Large Hadron Collider produces perhaps a few nanograms of antiprotons per year. The cost of producing a single gram of antimatter would exceed the gross domestic product of Earth. Even if production costs could somehow be reduced by factors of millions, safely storing antimatter for long-duration spaceflight poses fundamental engineering challenges. Antimatter must never contact ordinary matter or instant annihilation occurs. Theoretical propulsion systems, regardless of their energy source, all eventually confront the same fundamental barrier. The speed of light represents an absolute cosmic speed limit. Nothing with mass can reach or exceed this velocity. This limitation does not arise from engineering constraints or energy requirements. It represents a fundamental feature of space-time itself. Special relativity, Einstein's theory describing the relationship between space, time, and motion, reveals that velocity affects more than just position. As an object approaches light speed, several strange effects occur. The object's mass appears to increase from the perspective of stationary observers. Time aboard the moving object slows down relative to time experienced by stationary observers. Distances in the direction of motion appear to contract from the perspective of the moving object. These are not illusions or measurement errors. They represent genuine physical effects that have been verified through countless experiments over more than a century. Time dilation is not something that merely seems to happen. It actually happens. A clock moving at high velocity genuinely ticks more slowly than a stationary clock, and this difference can be measured with extraordinary precision. The mathematics of special relativity show that reaching light speed would require infinite energy. As velocity increases, the energy needed for further acceleration increases exponentially. Each additional increment of velocity requires more energy than all previous increments combined. By the time you reach 99% of light speed, acceleration becomes so energy intensive that even antimatter propulsion struggles to provide additional velocity. Reaching 100% would require literally infinite energy, which makes light speed an unreachable asymptote. This fundamental barrier appears to doom interstellar travel. If light speed cannot be reached, and if even approaching light speed requires energy resources far beyond current human capabilities, how could humanity ever hope to travel between stars during a single human lifetime? The answer lies in one of the most profound and counterintuitive features of relativity. Time dilation, the slowing of time for moving observers, creates a loophole in what initially appears to be an ironclad constraint. While light speed remains forever unreachable, and while observers on Earth would measure journey times in thousands or millions of years, travelers aboard a spacecraft moving at extreme velocities would experience far less subjective time. At 90% of light speed, time aboard the spacecraft passes at approximately 44% of the rate experienced by stationary observers. A journey that takes 10 years according to Earth clocks would feel like only 4.4 years to the travelers. This represents a noticeable but not dramatic difference. The traveler ages more slowly, but not dramatically so. At 99% of light speed, the difference becomes more significant. Time aboard the spacecraft passes at approximately 14% of Earth time. A 10-year journey, according to Earth clocks, would feel like only 1.4 years to the travelers. The travelers age less than 1.5 years, while more than a decade passes on Earth. At 99.9% of light speed, the effect becomes extraordinary. Time aboard the spacecraft passes at approximately 4.5% of Earth time. A 10-year journey according to Earth clocks would feel like only 5.5 months to the travelers. The travelers experience barely half a year of subjective time while a decade passes in the outside universe. The effect continues to amplify as velocity approaches light speed more closely. At 99.99% of light speed, a 10-year journey according to Earth clocks would feel like only 2 weeks to the travelers. At 99.999%, the same journey would feel like roughly 2 days. At 99.9999%, it would feel like less than 5 hours. This is not science fiction. This is established physics, verified by experiments so numerous and precise that the scientific community regards time dilation as completely uncontroversial. Particles accelerated to near light speed in particle accelerators live measurably longer before decaying compared to identical particles at rest. GPS satellites must account for time dilation effects, or they would provide increasingly inaccurate position measurements. Relativistic time dilation is as real as gravity, as verified as electromagnetism, as fundamental as quantum mechanics. The implications for space travel are staggering. At sufficiently high velocities, travelers could cross distances that light itself requires decades or centuries to traverse, while aging only months or years. The journey from the traveler's perspective collapses to a manageable duration. Subjective time, the time experienced by the traveler, becomes the relevant measure of journey length rather than the time measured by distant observers. Consider Proxima Centauri again, that nearest stellar neighbour 4.24 light-years from Earth. At constant acceleration of 1 Earth gravity, matching the acceleration we experience standing on Earth's surface, a spacecraft could reach the midpoint of the journey, flip over, and decelerate at 1 Earth gravity for the second half. This constant acceleration provides artificial gravity throughout the journey, eliminating the health problems associated with long-duration weightlessness. Under constant 1 gravity acceleration, the spacecraft would reach Proxima Centauri in approximately 3.6 years of ship time. The travelers would age less than 4 years while covering a distance light requires 4.24 years to cross. Meanwhile, approximately 6 years would pass on Earth. The travelers arrive younger than they would have if they had stayed home and experienced normal time progression. Traveling to Barnard's star, 6 light-years away, would require approximately 4.3 years of ship time under constant 1 gravity acceleration. Wolf 359, 7.9 light-years away, would take approximately 5 years of ship time. Sirius, 8.6 light-years distant, would require approximately 5.2 years of ship time. The traveller could reach any of these nearby stars within what amounts to a long but manageable journey, comparable to the duration of a college education. Extending the analysis to more distant destinations reveals even more dramatic possibilities. Alpha Centauri, Barnard's star, Wolf 359, and Sirius all lie within 10 light-years of Earth. Dozens of stars lie within 20 light-years. Hundreds lie within 50 light-years. Thousands lie within 100 light-years. Each of these destinations becomes theoretically reachable within what amounts to a significant but not impossible fraction of a human lifetime. The center of our galaxy lies approximately 26,000 light-years away. At constant 1 gravity acceleration, travelers could reach the galactic core in approximately 20 years of ship time. 20 years is a substantial commitment, roughly a quarter of an average human lifespan, but it remains entirely feasible. Travelers departing in their 20s would arrive in their early 40s, still young enough to explore and study whatever they discovered before attempting the return journey. The Andromeda Galaxy, our nearest large galactic neighbour, lies approximately 2.5 million light-years from Earth. At constant 1 gravity acceleration, travellers could reach Andromeda in approximately 28 years of ship time. 28 years represents more than a third of an average human lifetime, but remains well within human lifespan limits. Travellers departing in their early 20s could arrive in their early 50s, still possessing decades of potential life ahead of them. Even more distant destinations fall within reach of a single human lifetime when measured in subjective traveller time. The Virgo cluster, a massive collection of galaxies approximately 55 million light-years away, could be reached in approximately 30 years of ship time. The Coma cluster, approximately 300 million light-years distant, would require approximately 32 years of ship time. The observable edge of the universe, approximately 46 billion light-years away, would take approximately 45 years of ship time. These numbers reveal something profound about the structure of space-time. From the perspective of a traveller moving at extreme relativistic velocities, the entire observable universe compresses into distances crossable within a single human lifetime. The billions of light-years separating galaxies collapse into subjective years or decades. The cosmic distances that appear to impose absolute barriers when viewed from a stationary reference frame become manageable when viewed from a relativistic reference frame. The universe does not trap conscious observers in any particular location. Physics provides a pathway allowing biological entities to cross cosmic distances that would otherwise require geological timespans. The loophole is time dilation, the slowing of time for moving observers that allows subjective experience to compress journeys of millions or billions of years into decades of lived experience. However, this extraordinary capability comes with a price that physics imposes without exception or mercy. While the traveller experiences only years or decades of subjective time, observers on Earth experience every single year of the journey according to light travel time plus the time required for acceleration and deceleration. The traveller ages slowly. The universe ages normally. When the traveller arrives at their destination, millennia or millions of years may have passed in the broader cosmos. This creates a profound asymmetry between traveler time and universal time. Consider again the journey to the galactic core. The traveler experiences approximately 20 years of subjective time, but observers on Earth would wait approximately 26,000 years for the traveler to arrive at the destination. By the time the spacecraft reaches the galactic core, human civilization on Earth will have risen and fallen multiple times. The travelers would emerge into a future completely disconnected from the era they departed. If those travelers then returned to Earth, another 26,000 years would pass for Earth, while the travelers experienced another 20 years of subjective time. The round trip would consume approximately 40 years of traveler time, but 52,000 years of Earth time. The travelers would return to an Earth so transformed by time that nothing familiar would remain. Languages would have evolved beyond recognition. Continents would have shifted. Species would have evolved or gone extinct. Even the night sky would show different constellations as stars moved in their orbits around the galactic center. This temporal disconnect represents the true cost of relativistic space travel. The traveler could explore the cosmos, could visit distant stars and galaxies, could witness wonders beyond imagination, but they would do so at the cost of permanent exile from their own time. Every light year of distance traveled purchases years or centuries or millennia of temporal displacement. The faster you move, the more slowly you age, but the more rapidly the universe ages around you. The mathematics governing this relationship involve what physicists call the Lorentz factor, often represented by the Greek letter gamma. This factor describes how much time slows down for a moving observer compared to a stationary observer. At low velocities, gamma equals approximately 1, meaning time passes at essentially the same rate for both moving and stationary observers. As velocity increases toward light speed, gamma increases without limit, causing time dilation to become increasingly extreme. The formula for gamma is relatively simple. 1 divided by the square root of 1 minus velocity squared divided by light speed squared. When velocity equals 0, gamma equals 1, producing no time dilation. When velocity equals 90% of light speed, gamma equals approximately 2.3, meaning time aboard the spacecraft passes at roughly 43% of the rate experienced by stationary observers. When velocity equals 99% of light speed, gamma equals approximately 7, meaning time passes at roughly 14% of stationary time. At 99.9% of light speed, gamma equals approximately 22. At 99.99%, gamma equals approximately 70. At 99.999%, gamma equals approximately 224. The progression accelerates rapidly as velocity approaches light speed more closely. There is no upper limit to gamma. In principle, gamma could equal thousands, millions, or billions, allowing correspondingly extreme time dilation. This unlimited growth of gamma provides the mechanism allowing travel across arbitrary cosmic distances within a single human lifetime. Want to reach a galaxy 1 billion light-years away within 40 years of subjective time? Maintain a gamma factor of approximately 25 million throughout the journey. Time will slow down by this factor, compressing 1 billion years of outside time into 40 years of subjective experience. The challenge lies not in the physics, which permits such journeys without modification, but in the engineering required to achieve and maintain such extreme velocities. Reaching gamma values in the thousands or millions requires velocities so close to light speed that the difference becomes expressible only in terms of additional nines after the decimal point. 99.999999% of light speed. These velocities demand energy levels so extreme that even antimatter propulsion struggles to provide adequate thrust. Consider the energy requirements more carefully. A spacecraft accelerating at one Earth gravity requires continuous thrust throughout the journey. For the first half, the engines fire to accelerate toward the destination. For the second half, the engines fire in the opposite direction to decelerate and arrive at the destination with zero relative velocity. The total energy expenditure depends on both the mass of the spacecraft and the velocity achieved. Accelerating a 1-ton spacecraft to 99% of light speed requires energy equivalent to approximately 400 megatons of TNT. This equals roughly 8 times the yield of the largest nuclear weapon ever detonated. Accelerating the same spacecraft to 99.9% of light speed requires approximately 1,200 megatons equivalent. 99.99% requires approximately 4,000 megatons. The energy requirements increase exponentially as velocity approaches light speed more closely. These calculations assume perfect conversion of stored energy into kinetic energy, with no losses to waste heat or inefficiency. In reality, no propulsion system achieves perfect efficiency. Even antimatter rockets would waste significant energy as the annihilation products scatter in all directions rather than focusing perfectly into thrust. Accounting for realistic inefficiencies would multiply the energy requirements by factors of 10 or more. Furthermore, these energy calculations consider only the spacecraft's dry mass, not including propellant. A rocket must carry fuel, and that fuel adds mass that must also be accelerated. Even with antimatter propulsion, the most energy-dense fuel theoretically possible, reaching extreme relativistic velocities, requires fuel masses comparable to or exceeding the spacecraft's dry mass. The total system mass, spacecraft plus fuel, might reach hundreds of tons, even for a minimal probe. Accelerating hundreds of tons to extreme relativistic velocity requires energy resources that dwarf anything humanity currently commands. The total annual energy consumption of human civilization equals approximately 580 exajoules, roughly equivalent to 13,000 megatons of TNT. Accelerating a single large relativistic spacecraft might require a significant fraction of humanity's total annual energy output. Maintaining a fleet of such vessels would require energy resources orders of magnitude beyond current capabilities. These energy requirements explain why relativistic interstellar travel remains firmly in the realm of theoretical possibility rather than near-term engineering. We understand the physics. We know such journeys are permitted by natural law, but bridging the gap between physical possibility and practical capability demands advances in energy generation and propulsion that may require centuries of technological development. Even if energy constraints could somehow be overcome, other challenges complicate relativistic travel. At extreme velocities, even individual atoms become deadly projectiles. The interstellar medium, though incredibly sparse by earthly standards, contains approximately 1 hydrogen atom per cubic centimeter. A spacecraft moving at 99.99% of light speed would encounter these atoms at relative velocities indistinguishable from light speed. Each collision would release energy equivalent to multiple nuclear weapons. The spacecraft would require shielding massive enough to absorb this continuous bombardment without vaporizing. The shielding mass would add to the total system mass, increasing energy requirements and compounding the engineering challenges. Some concepts propose using powerful magnetic fields to deflect charged particles before they reach the hull, But such magnetic shielding would itself require enormous power systems and add additional mass. Cosmic rays present another hazard. These high-energy particles pervade the galaxy, accelerated to near light speed by supernovae and other violent cosmic events. At extreme velocities, the spacecraft would encounter cosmic rays from all directions at combined relativistic velocities. The radiation dose accumulated during even a relatively short journey might exceed safe limits unless travelers were protected by heavy shielding or some form of advanced radiation countermeasures. Navigation introduces additional complexity. At extreme relativistic velocities, stellar aberration causes stars to appear to shift position dramatically. The entire view forward compresses into a small circle directly ahead, while stars behind the spacecraft redshift into invisibility. Accurate navigation would require real-time course corrections based on relativistic calculations accounting for these distortions. Small errors compounded over light years could cause the spacecraft to miss its destination entirely. These engineering challenges, while severe, differ fundamentally from the laws of physics. Physics permits relativistic interstellar travel without exception. Engineering determines whether intelligent species can actually build the necessary systems. A civilization sufficiently advanced, with access to stellar-scale energy resources and materials science far beyond current capabilities, could overcome these obstacles. The barriers are technological, not physical. But even advanced technology cannot overcome the temporal consequences of extreme relativistic travel. Time dilation is not a bug to be fixed or a problem to be engineered away. It represents a fundamental feature of space-time, an inescapable consequence of traveling at extreme velocities. Every journey to a distant destination creates an unbridgeable temporal gap between traveler and origin. This temporal disconnection forces a crucial distinction between one-way and round-trip journeys. For one-way travelers willing to permanently abandon their origin point and everyone they knew, time dilation enables exploration throughout the observable universe. A lifetime of subjective time could carry travelers to the most distant galaxies currently visible through our telescopes. The travelers would age normally, while the universe they departed aged millions or billions of years. Such travelers would become, in effect, seeds planted in the cosmic soil. They would establish humanity's presence in distant regions, creating new branches of human civilization disconnected from Earth by gulfs of time too vast to bridge. They might encounter civilizations that evolved during the millions of years of their journey. They might arrive to find their destination galaxy transformed by stellar evolution or galactic collisions. They would explore not just space but time, emerging into futures unimaginably distant from the era they departed. For round-trip travelers hoping to return to Earth and reconnect with human civilization, time dilation imposes severe constraints. A journey to the galactic core and back would consume 52,000 years of Earth time, while the traveller aged 40 years. The Earth they returned to would bear no resemblance to the Earth they departed. Everything and everyone familiar would be gone, transformed beyond recognition by the passage of 50 millennia. Even modest interstellar journeys create significant temporal gaps. A round trip to Proxima Centauri, accelerating at 1 Earth gravity, would require approximately 7 years of traveller time, but approximately 12 years of Earth time. The temporal mismatch remains manageable. Friends and family would be older but still alive. Society would have changed but remained recognizable. The travellers could conceivably reintegrate into a civilization not dramatically different from the one they left. Round trips to stars dozens or hundreds of light years away create increasingly problematic temporal gaps. A journey to a star 50 light years distant might consume 15 years of traveler time, but more than a century of Earth time. The travelers would return to a world where everyone they knew had died of old age. Technology would have advanced. Political systems might have transformed. Languages would have evolved. The travelers would be strangers in a familiar location, temporal exiles in their own homeland. Round trips to other galaxies become essentially indistinguishable from one-way journeys when measured by their impact on the traveler's connection to origin. A round trip to Andromeda would consume approximately 56 years of traveler time, but 5 million years of Earth time. The travelers would return to an Earth so transformed by evolution and geological change that calling it the same planet would be technically correct, but meaningfully false. The travelers might return to find humanity extinct, replaced by descendant species. They might find Earth's continents reconfigured by plate tectonics. They might return to a planet whose biosphere had been entirely transformed by millions of years of evolutionary radiation. This distinction between one-way and round-trip journeys fundamentally shapes the question of how far a human could travel in one lifetime. The physics permits journeys spanning billions of light years, reaching the most distant galaxies currently observable. But the meaning of such journeys depends critically on whether return remains possible or desired. The observable universe extends approximately 46 billion light-years in every direction, representing the distance light has travelled since the Big Bang when accounting for cosmic expansion. This volume contains perhaps 2 trillion galaxies, each hosting hundreds of billions of stars. The total number of stars in the observable universe likely exceeds 1 septillion, a number so large it becomes meaningless to human intuition. Time dilation, in principle, permits a traveller to reach any of these galaxies within a single human lifetime measured in subjective years. The physics does not distinguish between nearby destinations and distant ones in terms of what is fundamentally possible. Maintaining sufficiently high gamma values throughout the journey compresses even the longest light travel times into manageable subjective durations. However, cosmic expansion introduces a subtle but crucial complication. The universe expands everywhere, stretching space itself between galaxies. This expansion means that distant galaxies recede from us at velocities that increase with distance. Galaxies sufficiently far away recede faster than light, not because they move through space at such velocities, but because the space between us and them expands faster than light can cross it. This creates what cosmologists call the cosmic event horizon. Galaxies beyond this horizon, currently located approximately 16 billion light-years away, are receding so rapidly that no signal we send today, even travelling at light speed, could ever reach them. The expansion of space carries them away faster than our signal can close the distance. These galaxies remain observable because their light was emitted billions of years ago when they were closer and not receding as rapidly. But they have crossed beyond any possibility of contact. A relativistic spacecraft faces the same limitation. Even moving at arbitrarily high velocity, arbitrarily close to light speed, the spacecraft cannot reach galaxies beyond the event horizon. The expansion of space outpaces the spacecraft's forward progress, stretching the intervening distance faster than velocity can close it. The cosmic event horizon represents an absolute boundary to exploration, imposed not by velocity limits or energy constraints, but by the expansion of space-time itself. This boundary means that despite time dilation's ability to compress journey times, not all observable galaxies can be reached. The majority of galaxies we currently observe have already crossed beyond the event horizon and will remain forever inaccessible. We can see their ancient light, but we cannot touch their shores. Their light arrives carrying information about conditions billions of years in the past, but the galaxies themselves now exist in regions of space-time causally disconnected from our own. The event horizon also recedes over time, but more slowly than the expansion rate. Galaxies currently near the horizon continue crossing beyond it, removing themselves from the accessible universe. Meanwhile, galaxies currently beyond the horizon do not return to accessibility. The expansion accelerates, driven by dark energy, ensuring that the accessible fraction of the universe continually shrinks. Billions of years in the future, all galaxies beyond our local group will have receded beyond the horizon, leaving future astronomers with a much smaller, observable, and accessible cosmos. For practical purposes, a traveller's maximum range depends on the cosmic event horizon. Galaxies within approximately 16 billion light-years remain theoretically reachable given sufficient velocity. Galaxies beyond that distance have already slipped beyond reach. No matter how fast you travel or how much time you are willing to spend, this represents an absolute physical limit, not a technological constraint that future civilizations might overcome. Within this accessible volume, however, time dilation permits extraordinary freedom of movement. A lifetime of subjective time could carry a traveller to galaxies billions of light-years distant. The Virgo supercluster, the massive collection of galaxy clusters that includes our own local group, extends across approximately 110 million light-years. The entire structure remains well within the cosmic event horizon, and therefore theoretically accessible within a human lifetime. The question of maximum travel distance therefore splits into two distinct considerations. What is the absolute maximum distance that physics permits, and what is the practical maximum that maintains some meaningful connection to human civilization? The absolute maximum distance, constrained only by the cosmic event horizon, and not by any consideration of return or communication with origin, reaches into the billions of light-years. A traveller willing to commit their entire life to maximum duration one-way travel, willing to age the full 8 or 9 decades of potential human lifespan while maintaining arbitrarily high gamma factors, could theoretically reach galaxies at the current cosmic event horizon. They would witness cosmic structures on the largest scales. They would see galaxy superclusters, the filamentary web-like structure of the cosmic large-scale arrangement. They would explore regions of space-time so distant that their light takes billions of years to reach Earth. Such travelers would never return. They would never communicate their findings back to Earth because the signal would take billions of years to arrive. They would exist as permanent pioneers, establishing human presence in the most remote regions accessible to consciousness. They would age normally, while the universe they departed aged billions of years. Everyone and everything they knew would be gone for eons before they arrived at their destination. The Earth itself might be gone, consumed by the sun's red giant phase billions of years in the traveller's future. The practical maximum distance depends on what constraints you impose on the journey. If you require that the traveller be able to send signals back to Earth that arrive while human civilization still exists, the maximum distance drops dramatically. Even if civilization survives millions or tens of millions of years, round-trip signal travel time limits exploration to distances of a few million light-years at most. This encompasses the local group of galaxies, including Andromeda and several dozen smaller satellite galaxies. If you require that the traveller actually return to Earth while something recognizable as human civilization still exists, the constraints tighten further. Even if we generously assume civilization survives 1 million years, an extraordinarily optimistic estimate given that our species has existed for only 300,000 years, round-trip travel time limits exploration to destinations within approximately 500,000 light-years. This encompasses our galaxy, some satellite dwarf galaxies, and perhaps the Magellanic Clouds. It excludes Andromeda and all other major nearby galaxies. If you require return within centuries rather than millennia, maintaining the possibility that the traveller's descendants or cultural continuity might persist, the accessible range shrinks to perhaps a few hundred light years. This includes thousands of nearby stars, but represents a tiny fraction of our galaxy and an infinitesimal portion of the accessible universe. These different constraints create radically different answers to the question of how far a human could travel. The physics permits extraordinary range. The constraints we impose based on what we value about the journey, whether we prioritize range over return, exploration over connection, discovery over belonging, determine the effective limits. Different travelers would make different choices. Some would prioritize maximum exploration, willingly accepting permanent temporal exile in exchange for reaching the farthest possible destinations. They would view time dilation not as a cost but as a tool, a mechanism enabling journeys that would otherwise require impossible spans of subjective time. They would embrace the role of cosmic seed, establishing humanity's presence throughout the accessible universe, regardless of whether they could ever share their discoveries with the civilization that enabled their journey. Others would prioritize connection and return, limiting their exploration to ranges that permit meaningful contact with origin. They would view the temporal gap created by extreme time dilation as too high a price to pay. They would prefer to explore closer regions more thoroughly, establishing networks of outposts and colonies within a volume of space where round-trip communication remains possible within reasonable timeframes. They would build an extended human civilization spanning perhaps hundreds or thousands of light years, maintaining cultural continuity across interstellar distances. Neither choice is objectively correct. They reflect different values, different priorities, different conceptions of what makes exploration meaningful. The universe does not care which path we choose. It offers the same physics to every traveller. What we do with that physics, which trade-offs we accept, which destinations we prioritise, remain fundamentally human decisions. The question of maximum travel distance ultimately becomes a question about identity and meaning. A traveller departing for a galaxy billions of light years away accepts permanent disconnection from everything that gave their life context. They will never again speak to another human who lived in their era. They will never share their discoveries with anyone who remembers the world they departed. They become, in a sense, a message in a bottle cast into the cosmic ocean, hoping perhaps that future intelligence will find them, but accepting that they may never be found. Such journeys require a particular psychology. The traveller must find meaning in exploration itself, disconnected from external validation or communication with origin. They must accept solitude on scales both spatial and temporal. They must be willing to be the last human of their era, carrying forward into an incomprehensibly distant future the memories and knowledge of a time that will be ancient history by the time they arrive at their destination. Not everyone possesses this psychology. Most humans derive meaning from connection, from relationships, from being part of communities that extend beyond individual existence. For such people, extreme one-way relativistic journeys offer no appeal, regardless of the extraordinary destinations they enable. The cost of permanent temporal exile exceeds any benefit that exploration might provide. But some humans do possess this pioneer psychology. Throughout history, individuals have undertaken journeys knowing they would never return, accepting permanent disconnection from origin in pursuit of discovery. The first humans to migrate out of Africa could not return. The Polynesians who sailed to remote Pacific islands aboard primitive canoes often could not return. Early European colonists traveling to the Americas generally never saw their homelands again. These were one-way journeys into unknown futures, accepted by people who valued discovery more than connection to origin. Relativistic interstellar travel represents the ultimate extension of this pattern. The physics permits journeys across scales that dwarf any terrestrial exploration. The temporal consequences create disconnections that exceed any historical precedent. But the fundamental human motivation, the willingness to trade familiar connections for unknown destinations, remains recognizable even when projected across cosmic distances. Understanding how far a human could travel in one lifetime, therefore, requires understanding what kind of journey we mean. One-way journeys permit exploration spanning billions of light years, reaching the current cosmic event horizon, witnessing galactic superclusters and the large-scale structure of the observable universe. Round-trip journeys with potential for return constrain exploration to much smaller volumes, perhaps a few hundred light years if return must occur within centuries, perhaps a few million light years if return within a million years suffices. The distinction matters because it determines what kind of future humanity might build beyond Earth. A future focused on one-way relativistic exploration would scatter human consciousness across the accessible universe, planting seeds that would never reconnect, establishing isolated outposts disconnected from each other by gulfs of space and time too vast to bridge. Each outpost would represent a separate evolutionary path, a unique branch of human development shaped by local conditions and the particular psychology of the pioneers who established it. A future focused on round-trip exploration and return would build an extended but continuous human civilization, spreading outward from Earth at rates that maintain communication and cultural continuity across interstellar distances. This civilization would grow more slowly in spatial extent, but maintain coherence across time. Knowledge gained at one outpost could be shared with all others. Cultural innovations could propagate throughout the network. Humanity would remain recognizably a single extended civilization rather than fragmenting into isolated evolutionary experiments. Both futures are physically possible. Both involve trade-offs between different values. Maximum spatial extent requires accepting temporal disconnection. Cultural continuity requires accepting spatial constraints. We cannot have both simultaneously. Physics does not permit civilizations that maintain cultural continuity while spanning billions of light years. The temporal consequences of relativistic travel make such continuity impossible. The universe imposes these trade-offs without exceptions. You can explore anywhere within the cosmic event horizon, given sufficient velocity and willingness to accept the temporal consequences. But you cannot explore everywhere while maintaining connection to everywhere else. You must choose which matters more: how far you go or whether you can return, maximum range or continued relationship. These choices shape the ultimate answer to our original question: how far could a human actually travel in one lifetime? The physics permits journeys spanning billions of light years. A properly equipped spacecraft maintaining arbitrarily high gamma factors throughout the journey could carry a traveler to galaxies at the current cosmic event horizon, while the traveler aged only decades. The universe places no fundamental barrier preventing such journeys beyond the expansion of space-time itself. But the meaningful question asks not what physics permits, but what humans would choose. Would we prioritize maximum exploration, accepting permanent temporal exile? Would we prioritize connection and return, limiting exploration to nearby regions? Would different groups make different choices, some becoming cosmic pioneers while others build extended continuous civilizations? These questions have no single answer because they depend on values rather than physics. Different individuals and different cultures would answer differently based on what they consider meaningful about exploration. The universe accommodates all these different choices. It offers pathways to the most distant galaxies for those willing to pay time dilation's price. It offers more modest but connected exploration for those who value relationship with origin over maximum range. Understanding these possibilities and their implications matters because humanity stands at the threshold of becoming an interstellar species. We have not yet developed the propulsion technology necessary for relativistic travel. We remain bound to our solar system by current engineering limitations. But nothing in physics prevents us from eventually developing such technology. The journey from current capabilities to relativistic interstellar travel represents an engineering challenge, not a physical impossibility. When humanity does develop relativistic propulsion, assuming we survive long enough as a species to achieve this technological threshold, we will confront these questions about range versus return, exploration versus connection. We will need to decide what kind of interstellar civilization we want to build. We will need to choose between maximum spatial extent and cultural continuity. We will need to determine whether we view time dilation as a tool enabling extraordinary exploration or as a cost that severs travelers from their origins. These decisions will shape human destiny for millions or billions of years. They will determine whether humanity remains a single, continuous civilization spreading gradually outward from Earth, or fragments into isolated evolutionary experiments scattered across cosmic distances. They will define what it means to be human in a spacefaring context, whether identity remains tied to origin or transforms into something more fluid and disconnected from specific locations and eras. The universe you currently inhabit extends 46 billion light-years in every direction. It contains structures so vast that light requires billions of years to cross them. From your position on this small planet, you observe cosmic distances that require numbers with 24 digits to express in miles. The scale exceeds not just human experience, but human cognitive capacity. We cannot truly comprehend how far the universe extends. Yet within a single human lifetime, properly equipped with technologies we can imagine but have not yet built, a human being could theoretically cross significant fractions of that incomprehensible expanse. The universe has not constructed walls around humanity. It has provided highways stretching toward every horizon, highways we have not yet learned to travel, but that physics declares open to anyone who can master the necessary velocity. How far could a human actually travel in one lifetime? The answer depends on what we are willing to build, what we are willing to sacrifice, what we are willing to invest across generations. It depends on whether we value range over return, exploration over connection, discovery over belonging. It depends on choices that physics cannot make for us. Choices that remain fundamentally human, even when their consequences span cosmic distances. The stars are not impossibly distant. They merely wait for us to develop the means of reaching them. The galaxies are not forever beyond our grasp. They require only sufficient velocity and sufficient willingness to accept the temporal consequences of the journey. Within the equations that govern motion through space-time lies a promise that distances measured in millions of light-years could someday fall within the reach of a single human life. That promise exists in the mathematics of relativity, verified by a century of experiments, waiting for the engineering that would transform theoretical possibility into practical capability. The universe invites exploration, and somewhere between the 400 and 30,000 miles per hour we have achieved, and the velocities where gamma exceeds millions, lies a threshold where human cosmic exploration transforms from fantasy into reality. The distance a human could travel in one lifetime is not ultimately limited by physics. It is limited only by our imagination, our determination, and our willingness to pay the price the universe demands for passage to the stars. This effect, known as time dilation, seemed absurd when first proposed. How could time, that most fundamental and universal of quantities, flow at different rates depending on your velocity? Yet the mathematics proved inescapable, and within decades, experiments confirmed what Einstein had derived from pure logic. Time dilation is real, it can be measured, and it transforms everything we thought we understood about the limits of human exploration. The relationship between velocity and time dilation follows a precise mathematical formula. Einstein introduced a quantity that physicists call gamma, the Lorentz factor. This number tells you exactly how much time slows down at any given velocity. To calculate gamma, you divide 1 by the square root of 1 minus your velocity squared divided by the speed of light squared. The formula looks intimidating, but it yields numbers that could change the fate of interstellar travelers. At everyday velocities, gamma barely differs from 1. A car traveling at highway speed experiences time dilation so minuscule that even the most precise atomic clocks can barely detect it. An aeroplane passenger ages perhaps a few nanoseconds less than someone who stayed on the ground during a cross-country flight. The effect exists, but carries no practical significance for terrestrial life. The transformation begins when velocity climbs toward a substantial fraction of light speed. At 50% of light speed, gamma reaches 1.15. Time aboard the spacecraft passes about 15% slower than time on Earth. 1 year of ship time corresponds to roughly 14 months of Earth time. Noticeable, but not transformative. At 90% of light speed, gamma jumps to approximately 2.3 for every year that passes aboard the speeding vessel. 2 years and 4 months pass on Earth. A 50-year journey at this velocity would see the traveller age 50 years, while Earth aged 115 years. The crew would return to find their grandchildren elderly and their great-grandchildren running the world. Pushed to 99% of light speed, and gamma reaches 7.1. The transformation accelerates dramatically. 7 years pass on Earth for every year experienced by the traveller. A decade of ship time corresponds to 70 years of Earth time. A journey lasting 50 subjective years would span 355 years of Earth history. You would depart from one civilization and return to find an entirely different world. At 99.9% of light speed, gamma exceeds 22. 22 years of Earth time compress into a single year aboard the spacecraft. The disparity has grown enormous. 50 years of travel would span 1100 years on Earth. The Roman Empire fell less than 1600 years ago. A journey of this duration would cross time spans comparable to the rise and fall of entire civilizations. The mathematics continue relentlessly as velocity approaches light speed ever more closely. At 99.99%, gamma exceeds 70. At 99.999%, gamma surpasses 223. At 99.9999%, gamma climbs past 707. Each additional 9 added to the velocity pushes the time dilation factor higher by roughly a factor of 3. These numbers transform the question of interstellar travel. Consider a journey not to the nearest star, but to somewhere more distant. Vega, one of the brightest stars in our night sky, lies approximately 25 light-years from Earth. At conventional spacecraft velocities, reaching Vega would require hundreds of thousands of years. no human could survive even a tiny fraction of such a journey. But at 99% of light speed, with gamma at 7.1, the calculation transforms completely. From Earth's perspective, the journey takes approximately 25 years and 3 months. Light speed is light speed, and you cannot exceed it. But from the traveller's perspective, time dilation compresses this duration by a factor of 7. The subjective journey time drops to roughly 3.5 years. You could travel to Vega, spend time exploring any planets orbiting that brilliant blue-white star, and return to Earth having aged only 7 years, while 50 years passed at home. Push velocity to 99.9% of light speed, and the numbers become even more remarkable. Gamma, at 22, compresses that same 25-year journey to barely over 1 year of subjective time. You could visit Vega and return before your second birthday aboard the ship. Earth would age 50 years during your round trip, but you would age only 2. The Pleiades star cluster, that famous grouping of hot blue stars visible to the naked eye in winter skies, lies approximately 440 light-years from Earth. At conventional speeds, reaching the Pleiades would require millions of years. At 99.99% of light speed, with gamma exceeding 70, the subjective journey time drops to approximately 6 years. You could travel to one of the most famous star clusters in human mythology, explore multiple stellar systems within the cluster, and return having aged perhaps 15 years, while Earth aged nearly 900 years. The center of our galaxy lies approximately 26,000 light-years away. A black hole containing 4 million times the mass of our Sun lurks there, surrounded by dense star clusters and violent phenomena found nowhere else in the Milky Way. At 99.999% of light speed, with gamma exceeding 223, the subjective journey time falls to approximately 116 years, still longer than a human lifetime, but within reach of a multi-generational crew or travelers willing to accept life extension technologies that might emerge in coming centuries. Pushed to 99.9999% of light speed, with gamma exceeding 700, and the galactic center becomes reachable in approximately 37 years of ship time. A traveler could leave Earth at age 25, journey to the supermassive black hole at the heart of our galaxy, conduct observations impossible from Earth, and arrive having aged to 62. They would return to find that over 52,000 years had passed on Earth, but they themselves would have lived a normal human lifespan. The Andromeda Galaxy presents the ultimate test of relativistic travel within what we might call the local universe. At 2.5 million light-years distance, Andromeda represents the nearest major galaxy to our own. Its trillion stars form a spiral structure larger than the Milky Way, potentially harboring countless worlds and perhaps other civilizations. No conventional propulsion could ever bridge this gap within any meaningful time frame. Yet, at velocities where gamma reaches 1 million, achievable only at speeds so close to light that the difference becomes almost philosophical, the subjective journey time to Andromeda drops to approximately 2.5 years. A traveler could cross the void between galaxies, explore an entirely separate island universe, and experience the journey as lasting less time than a typical doctoral program. Earth would age 2.5 million years during this journey. Human civilization would likely be unrecognizable or extinct upon return, but the traveler themselves would have aged only a few years. These calculations reveal a profound truth that Einstein's equations encode, but everyday experience obscures. The universe has not designed barriers to prevent cosmic exploration. Time dilation provides a mechanism that could carry human consciousness across distances that light itself requires millions of years to traverse. The limiting factor is not physics, but engineering. The equations permit interstellar and even intergalactic travel within a human lifetime. We simply lack the technology to achieve the necessary velocities. But why do these extraordinary velocities require such extraordinary energy? The answer lies in another of Einstein's revolutionary insights, encoded in the most famous equation in physics. E equals mc squared tells us that mass and energy are equivalent, interchangeable aspects of the same underlying reality. This equivalence has consequences for anything attempting to move at relativistic velocities. As an object accelerates, it gains kinetic energy. At low velocities, this energy increase follows the familiar patterns Isaac Newton described centuries ago. Doubling your velocity quadruples your kinetic energy. The relationship is straightforward and places no fundamental limits on how fast you can go, provided you have enough fuel. But as velocity approaches a significant fraction of light speed, something strange happens. The energy required to accelerate further begins climbing faster than Newton's equations predict, much faster. The object begins behaving as though it has more mass than it started with. This effect, called relativistic mass increase, grows more pronounced as velocity increases. At 50% of light speed, an object behaves as though it has about 15% more mass than it possesses at rest. The extra energy you pump in to accelerate further seems to disappear into this mass increase rather than producing proportional velocity gains. At 90% of light speed, the effective mass has more than doubled. The same engine thrust that once produced rapid acceleration now yields sluggish response, as though the spacecraft had suddenly grown enormously heavy. At 99% of light speed, the effective mass has increased by a factor of 7. At 99.9%, the factor exceeds 22. Each increment of additional velocity requires not just more energy, but exponentially more energy. The relationship follows the same gamma factor that governs time dilation, but working against the traveller rather than for them. This mass increase explains why the speed of light represents an absolute barrier for any object possessing rest mass. As velocity approaches light speed, effective mass approaches infinity. Accelerating an infinite mass would require infinite energy. Since infinite energy does not exist, the final approach to light speed becomes asymptotic. You can get closer and closer, adding 9 after 9 to your velocity expressed as a percentage of light speed, but you can never quite arrive. The practical energy requirements for relativistic travel are staggering, even at velocities far below this theoretical limit. Consider accelerating a small probe massing perhaps 1,000 kilograms to 90% of light speed. The kinetic energy required exceeds 10 to the 19th joules. Written out, this number contains 20 digits. It equals the total energy output of our Sun for approximately 2 seconds, or the entire energy consumption of human civilization for roughly 1 million years, concentrated into accelerating a single small spacecraft. For a crewed vessel capable of supporting human life during an interstellar journey, the mass might reach 100,000 kilograms or more. The energy requirement scales proportionally. Accelerating such a vessel to 90% of light speed would require energy equivalent to the Sun's total output for several minutes. This is not an engineering limitation awaiting a clever solution. It is a fundamental requirement imposed by the structure of space-time itself. The energy cost doubles when you remember that travelers generally want to stop when they arrive. Decelerating from 90% of light speed requires exactly as much energy as accelerating to that velocity in the first place. A round trip doubles the requirement again. A journey to Vega and back at 90% of light speed would require 4 times the energy needed for one-way acceleration. an amount exceeding the sun's output for a quarter hour. These energy requirements explain why relativistic travel remains theoretical, despite the physics being well understood for over a century. No propulsion system humanity has ever built, tested, or seriously proposed can deliver energy on these scales. Chemical rockets fall short by a factor of billions. Nuclear fission improves the picture, but remains hopelessly inadequate. Even nuclear fusion, the process that powers the sun, struggles to provide the energy density necessary for practical relativistic propulsion. The acceleration profile for relativistic travel introduces additional constraints. Humans can tolerate continuous acceleration at one Earth gravity indefinitely. This feels like normal weight, allowing travelers to walk, eat, sleep, and function normally throughout the journey. Higher accelerations become uncomfortable and eventually dangerous. Sustained acceleration at 2 gravities causes fatigue and health problems. 5 gravities can cause blackouts. 10 gravities can be fatal. At 1 gravity of continuous acceleration, a spacecraft would reach 90% of light speed in approximately 11 months. The first half of this acceleration phase carries you toward your destination while building velocity. At the midpoint of your journey, you would flip the spacecraft and begin decelerating at 1 gravity, arriving at your destination with 0 relative velocity after the same duration of braking. This constant acceleration profile changes the journey time calculations. Rather than reaching high velocity quickly and coasting, you spend the entire journey either accelerating or decelerating. For short trips, this approach requires more energy than a coast phase would demand. For very long journeys, the constant acceleration approach actually saves time by maintaining thrust throughout rather than coasting at a fixed velocity. 1 year of acceleration at 1 Earth gravity would bring a spacecraft to approximately 77% of light speed. 2 years would reach approximately 97%. 3 years would exceed 99%. The velocity gains slow as you approach light speed, with each additional year of acceleration adding smaller increments. But time dilation compensates, compressing the subjective journey time even as acceleration efficiency drops. The twin paradox emerges naturally from these relativistic considerations and deserves careful examination because it illustrates just how profoundly time dilation affects human experience. Imagine 2 identical twins, Alice and Bob. Alice boards a relativistic spacecraft and travels to a star 20 light-years distant at 90% of light speed. Bob remains on Earth. From Bob's perspective on Earth, Alice's outbound journey takes approximately 22 years. Her return journey takes another 22 years. Bob ages 44 years waiting for his twin to return, growing from a young adult to retirement age during Alice's absence. From Alice's perspective aboard the spacecraft, time dilation compresses each leg of the journey. At 90% of light speed, gamma equals approximately 2.3. Her 22-year outbound journey feels like only 9.5 years. Her return journey feels like another 9.5 years. Alice experiences only 19 years of travel, while Bob experiences 44. When Alice returns to Earth, she is 19 years older than when she left. Bob is 44 years older. The twins, who were born on the same day, are now separated by 25 years of biological age. Alice's hair might show the first hints of grey, while Bob's has gone completely white. Alice might still be building her career, while Bob is planning retirement. This scenario troubled early critics of relativity, who argued that motion is relative. From Alice's perspective, Bob was the one moving away and then returning. Why should Alice age less rather than Bob? The resolution lies in the asymmetry of their experiences. Alice experienced acceleration when her spacecraft changed velocity. Bob experienced no acceleration. This asymmetry breaks the equivalence between their reference frames and determines who ages less. The twin paradox has been verified experimentally using precise atomic clocks. In 1971, physicists Joseph Hafele and Richard Keating flew cesium atomic clocks around the world on commercial airliners, comparing them to identical clocks that remained stationary. The flying clocks gained approximately 270 nanoseconds compared to the stationary clocks, exactly as special relativity predicted. The effect was tiny because airplane velocities are tiny compared to light speed. But the effect was real, measurable, and confirmed Einstein's century-old predictions. Time dilation creates strange possibilities for relativistic travelers beyond simple aging differences. Information from Earth could reach travelers during their journey, allowing them to receive news, entertainment, and personal messages from home. But the travelers would receive this information compressed in time, with years of Earth broadcasts arriving during months of ship time. They could watch decades of Earth history unfold during their journey, seeing children grow to adults and adults grow old in accelerated playback. Communication in the opposite direction faces different challenges. Messages sent from the spacecraft would take years to reach Earth, and Earth's responses would take years to return. A traveller at 99% of light speed, journeying to a star 100 light-years distant, would experience the trip in approximately 14 years. But any message sent from the spacecraft 1 year into the journey would take decades to reach Earth, and Earth's reply would not arrive until long after the traveller had reached their destination. The visual experience of relativistic travel would be equally strange. Light arriving from ahead of the spacecraft becomes blue-shifted, its frequency increased by the Doppler effect created by the spacecraft's motion toward the source. Stars ahead would shift from their normal colors toward blue, then ultraviolet, then X-ray frequencies as velocity increases. The familiar constellations would become sources of invisible radiation, detectable only through specialized instruments. Light from behind the spacecraft experiences the opposite effect. Stars in the rear become redshifted, their light stretched to longer wavelengths. They would shift from visible colors to infrared, then to radio frequencies, eventually becoming undetectable as their radiation dropped below any instrument sensitivity. Relativistic aberration further distorts the traveler's view. Light arriving from the sides of the spacecraft appears to come from ahead, compressed into a narrowing cone in the direction of travel. At 90% of light speed, this effect bunches most of the visible universe into a circle spanning roughly 60 degrees ahead of the spacecraft. At 99% of light speed, this circle shrinks to approximately 16 degrees. At even higher velocities, the entire cosmos collapses into a brilliant point of light directly ahead, with utter darkness behind. The interstellar medium presents hazards that grow more severe with increasing velocity. Space between stars is not perfectly empty. Each cubic centimetre contains approximately 1 hydrogen atom on average, along with traces of helium, heavier elements, and dust particles. At low velocities, this material poses no threat. Spacecraft pass through it like bullets through air, barely noticing its presence. At relativistic velocities, this sparse material transforms into a deadly radiation environment. Each hydrogen atom strikes the spacecraft with kinetic energy proportional to the gamma factor squared. At 90% of light speed, each hydrogen atom impact delivers energy comparable to cosmic ray particles. At 99% of light speed, the energy increases by another factor of 20. The spacecraft's forward surfaces would be bombarded by a continuous sleet of high-energy particles capable of damaging electronics, degrading materials, and penetrating biological tissue. Shielding against this radiation requires either massive physical barriers or active deflection systems. Magnetic fields could potentially sweep charged particles away from the spacecraft, though the field strengths required grow with velocity. Physical shielding adds mass that must itself be accelerated to relativistic velocities, compounding the energy requirements. Despite these formidable challenges, the physics of relativistic travel remains clear and verified. Time dilation is not a theoretical curiosity, but a measured phenomenon confirmed by decades of precision experiments. The equations permit human travel across interstellar and even intergalactic distances within a single biological lifetime. The barrier is not physics, but propulsion technology. What technologies might actually achieve the velocities necessary to exploit time dilation? What engines could deliver the stupendous energy requirements relativistic travel demands? Let us now examine the propulsion concepts that could transform these mathematical possibilities into engineering realities. From nuclear explosions to antimatter annihilation to beams of light pushing gossamer sails across the cosmos. The gap between current spacecraft velocities and the speeds necessary for interstellar travel within a human lifetime spans an almost incomprehensible gulf. Our fastest probes crawl through space at roughly 1/10,000th of light speed. Meaningful time dilation begins only above 10% of light speed and becomes truly transformative only above 90%. Crossing this velocity chasm requires propulsion concepts that transcend anything humanity has yet constructed, tested, or even fully designed. Consider the scale of the challenge. The Parker Solar Probe travels at approximately 0.06% of light speed during its closest solar approaches. Reaching 10% of light speed, the threshold where relativistic effects become noticeable, requires increasing velocity by a factor of roughly 170. Reaching 90% of light speed, where time dilation dramatically compresses journey times, requires a velocity increase of 1,500 times beyond our current maximum. This is not an incremental engineering improvement. This is a revolution in propulsion technology that must bridge 6 orders of magnitude. Yet humanity has conceived propulsion concepts that could potentially cross this gulf. Some require only engineering development using known physics. Others demand breakthroughs in materials, science, or energy production. A few push into speculative realms where the physics itself remains uncertain. Understanding these concepts reveals both the possibilities and limitations of interstellar travel within human lifetimes. Nuclear pulse propulsion represents perhaps the most audacious propulsion concept ever seriously studied by mainstream engineers. The idea emerged in the late 1950s at the General Atomics Laboratory in San Diego, where a team of brilliant physicists asked a question that seemed insane on its surface. What if you could harness nuclear explosions for spacecraft propulsion? What if, instead of containing nuclear energy within a reactor, you simply detonated bombs behind your spacecraft and rode the blast waves to the stars? Project Orion, as the effort became known, attracted some of the finest scientific minds of the era. Freeman Dyson, Theodore Taylor, and dozens of other physicists and engineers devoted years to transforming this seemingly absurd concept into detailed engineering plans. They were not dreamers spinning fantasies. They were serious scientists performing rigorous calculations and conducting actual experiments. The basic Orion concept works as follows. A spacecraft carries a large supply of nuclear explosive devices, essentially specially designed bombs. These devices are ejected one at a time from the rear of the spacecraft and detonated at a carefully calculated distance. The explosion creates a plasma fireball that expands outward in all directions. A massive pusher plate at the rear of the spacecraft absorbs the momentum from the fraction of this plasma that strikes it, pushing the vessel forward. Shock absorbers between the pusher plate and the crew compartment smooth out the violent impulses into tolerable acceleration. The Project Orion team conducted actual tests using conventional chemical explosives rather than nuclear devices. They built small models with pusher plates and detonated charges beneath them, demonstrating that the concept worked in practice. The models flew. The pusher plates survived repeated blasts. The shock absorption systems functioned as designed. Nuclear test ban treaties halted the program in 1963 before atomic detonations could be tested, but the physics had been validated. Calculations showed that Orion could achieve performance far exceeding any other propulsion concept then envisioned or since constructed. A modest Orion spacecraft using fission bombs could reach velocities of 3 to 4% of light speed. Larger designs incorporating hydrogen fusion bombs could potentially achieve 8 to 10% of light speed. The most ambitious designs, requiring engineering capabilities beyond 1960s technology, might reach 15% of light speed or higher. At 10% of light speed, the journey to Tau Ceti, a sun-like star approximately 12 light-years distant that may host potentially habitable planets, would require roughly 120 years. Still longer than a human lifetime, but within range of multi-generational missions or travelers willing to spend most of their existence in transit. Time dilation at this velocity provides minimal benefit, compressing the journey by only about 0.5%. The spacecraft would experience essentially the same duration as observers on Earth measure. The engineering challenges for nuclear pulse propulsion remain formidable but not insurmountable. The pusher plate must survive repeated exposure to nuclear fireballs without ablating away or cracking under thermal stress. The shock absorbers must function reliably through thousands of detonation cycles. The nuclear devices themselves must be designed for maximum thrust efficiency rather than maximum explosive yield. These problems require advanced engineering, but involve no unknown physics. Political and environmental concerns present more serious obstacles. Detonating thousands of nuclear devices, even in deep space far from Earth, raises questions about radioactive contamination and the weaponization of space technology. The Partial Nuclear Test Ban Treaty of 1963, signed during the height of Cold War tensions, specifically prohibits nuclear explosions in outer space. Any Orion Star spacecraft would require either treaty modifications or assembly in deep space far from Earth using devices launched separately from the pusher plate assembly. Despite these challenges, nuclear pulse propulsion remains one of the few propulsion concepts that could be built using current or near-term technology. No breakthrough physics is required. No exotic materials beyond existing capabilities are needed. The engineering is difficult but feasible. An Orion spacecraft could be designed, built, and launched within decades if humanity chose to commit the resources and navigate the political complications. Fusion propulsion offers potential performance improvements beyond fission-based systems. Nuclear fusion, the process that powers stars, including our Sun, combines light atomic nuclei into heavier ones, releasing enormous energy in the process. Fusion reactions produce several times more energy per unit mass than fission reactions and generate far less radioactive waste. A fusion rocket could theoretically achieve exhaust velocities high enough to enable 20 to 30% of light speed with reasonable fuel mass fractions. However, fusion propulsion faces a challenge that has frustrated physicists for decades. Achieving controlled fusion requires heating fuel to temperatures exceeding 100 million degrees Celsius and confining this superheated plasma long enough for fusion reactions to occur. Despite 70 years of intensive research and billions of dollars in investment, humanity has yet to demonstrate a fusion reactor that produces more energy than it consumes. Recent breakthroughs at facilities like the National Ignition Facility have achieved fusion ignition, but scaling these results to practical propulsion systems remains a distant goal. Several fusion rocket concepts have been proposed. The most promising involve using magnetic fields to confine the fusion plasma and direct the exhaust for thrust. Alternative approaches use laser-driven implosion of fusion pellets or antimatter catalysis to trigger fusion reactions. All face immense technical challenges in materials that can withstand the intense radiation and heat in magnetic field generation, requiring superconducting magnets and massive power supplies, and in fuel cycling systems that can maintain continuous fusion reactions for months or years. Even if fusion propulsion becomes feasible, it would likely provide velocities in the 10 to 30% of light speed range. Useful for interstellar missions to nearby stars, but insufficient for truly relativistic travel, where time dilation becomes dramatically effective. A journey to Alpha Centauri at 20% of light speed would require approximately 22 years, with minimal time dilation effects. The traveller would age essentially the same 22 years as observers on Earth. Antimatter represents the theoretical ultimate in energy density. When matter and antimatter collide, they annihilate completely, converting 100% of their combined mass directly into energy. An antimatter rocket could theoretically achieve exhaust velocities approaching the speed of light itself. The challenges are severe. Current production rates are infinitesimal. The cost exceeds trillions of dollars per gram. Storage requires perfect containment that cannot fail. Any breach would result in catastrophic explosion. Despite these obstacles, antimatter propulsion remains theoretically possible. The barriers are entirely technological and economic. One exotic variation on antimatter propulsion involves using antimatter not as fuel itself, but as a catalyst to trigger fusion reactions. Tiny amounts of antimatter injected into fusion fuel pellets could initiate fusion at much lower temperatures and pressures than pure fusion systems require. This antimatter catalyzed fusion propulsion would need far less antimatter than pure antimatter rockets, perhaps making the concept more feasible with advanced but not impossible technology. Laser sailing offers a radically different approach. Rather than carrying fuel, a laser sail is pushed by external power beamed from a distant source. A massive laser array focuses an intense beam onto an enormous reflective sail. The photon pressure accelerates the sail toward the target star. Calculations suggest laser sails could reach 20 to 40% of light speed. However, the challenges are substantial. The laser must generate immense power for years. The sail must be extraordinarily large, yet lightweight. Most critically, laser sails cannot decelerate at their destination. Breakthrough Starshot proposes using this approach to send gram-scale probes to Alpha Centauri at 20% of light speed. Even more speculative concepts push into uncertain physics. Warp drives and wormholes require exotic matter never observed in nature. Most physicists consider these mathematical curiosities rather than viable propulsion. Assuming humanity eventually develops practical propulsion technology, the question returns: how far could a human actually travel in one lifetime? The answers depend critically on one-way versus round-trip journeys. For travelers willing to accept permanent exile from their origin, time dilation enables exploration throughout the observable universe. Subjective lifetimes, measured in decades, could carry travelers to galaxies billions of light-years distant. Such travelers could witness the large-scale structure of the universe directly. They could explore galaxy superclusters. The price would be complete temporal disconnection from origin. Some individuals might embrace this role. Throughout history, certain people have demonstrated willingness to permanently leave everything familiar in pursuit of exploration. The Polynesian navigators who sailed to remote Pacific islands, often unable to return due to prevailing winds and currents, chose discovery over connection to origin. Early colonists departing for distant lands on one-way voyages accepted permanent exile from their homelands. Relativistic one-way journeys represent the ultimate extension of this pioneer psychology, magnified to cosmic scales. For round-trip travelers hoping to maintain connection to human civilization, time dilation imposes stricter constraints. The traveler experiences decades while Earth ages millennia. Everything they knew would be gone. Shorter journeys create manageable temporal gaps. A round trip to Proxima Centauri would span approximately 12 years of Earth time, while the traveler aged 7 years. Friends and family would be older but alive. Different individuals would weight these trade-offs differently. The expansion of the universe introduces an additional complication that further limits the accessible range of cosmic exploration. The universe is not static. Space itself expands, carrying distant galaxies away from us at velocities that increase with distance. This expansion means that light from very distant galaxies takes longer to reach us than simple division of distance by light speed would suggest, because the space the light travels through expands during its journey. At sufficiently large distances, galaxies recede faster than light can approach them. This does not violate relativity, because the galaxies are not moving through space at these velocities. Rather, the space between us and them is expanding at rates that exceed the speed of light. Light departing from such galaxies finds itself swimming against a current that carries it backward faster than it can swim forward. This effect creates what cosmologists call the cosmic event horizon, currently located approximately 16 billion light-years away. Galaxies beyond this horizon are receding so rapidly that no signal we send today, even at light speed, could ever reach them. The expansion rate exceeds our signal's forward progress. These galaxies remain observable because we see ancient light emitted billions of years ago when they were closer and the expansion rate was lower, but they have crossed beyond any possibility of contact. Even a spacecraft traveling at arbitrarily high velocity, arbitrarily close to light speed, cannot reach galaxies beyond the event horizon. The expansion of space itself outpaces the spacecraft's forward motion, stretching the intervening distance faster than velocity can close it. This represents an absolute limit to exploration, imposed not by energy constraints or technological barriers, but by the fundamental dynamics of cosmic expansion. The event horizon recedes over time, but more slowly than the expansion rate. Galaxies currently near the horizon continue crossing beyond it at an accelerating pace, driven by dark energy that causes the expansion rate itself to increase. Meanwhile, galaxies currently beyond the horizon do not return to accessibility. The net effect is a gradually shrinking fraction of the universe remaining within reach. Billions of years in the future, all galaxies beyond our local group, a collection of several dozen galaxies, including the Milky Way and Andromeda, bound together by mutual gravitation, will have receded beyond the event horizon. Future astronomers, in that distant era, would observe a much smaller, accessible universe, with the vast majority of currently visible galaxies having disappeared beyond any possibility of contact or even observation. For practical purposes, this cosmic event horizon defines the absolute maximum range of exploration. Within approximately 16 billion light-years, galaxies remain theoretically reachable given sufficient velocity. Beyond that distance, exploration becomes fundamentally impossible regardless of technology. This limit encompasses perhaps 1/1,000,000th of all galaxies in the observable universe. The overwhelming majority of cosmic structure has already crossed beyond reach. Within the accessible volume, however, time dilation permits extraordinary freedom of movement. The Virgo supercluster, that massive collection of galaxy clusters that includes our local group, extends across approximately 110 million light-years. The entire structure remains well within the cosmic event horizon and therefore theoretically accessible within a human lifetime measured in subjective years. A traveler maintaining sufficiently high velocity, with gamma factors in the millions, could theoretically cross these vast distances while aging only decades. The mathematics permits journeys to the most remote accessible regions of space-time within what amounts to a normal human lifespan for the traveler. The universe does not trap biological consciousness in any particular location. Physics provides pathways, allowing subjective experience to traverse cosmic scales. The final question concerns not what physics permits, but what humans would choose. Given the capability to reach distant galaxies at the cost of permanent temporal exile, would we? Given the option to explore nearby stars while maintaining connection to human civilization, would that limited range satisfy our curiosity? What destinations justify what sacrifices? What discoveries merit what costs? These questions have no universal answers because they depend on values that vary among individuals and cultures. The physics is neutral. Time dilation operates identically regardless of whether travelers embrace or regret the temporal consequences. The universe offers the same relativistic effects to every observer, caring nothing for human hopes or fears about temporal disconnection. What we do with these physical possibilities remains fundamentally a human decision. Some individuals possess psychology suited for permanent temporal exile. They derive meaning from exploration itself, disconnected from external validation or communication with origin. They would embrace the role of cosmic pioneer, carrying human consciousness to the most remote regions accessible to biological intelligence, accepting that they will never share their discoveries with the civilization that enabled their journey. Others require connection and community to find meaning in exploration. They need the possibility of return, of sharing discoveries, of contributing to the larger human project. For such individuals, the temporal disconnection created by extreme relativistic travel represents too high a price. They would prefer exploring closer regions more thoroughly, building networks of outposts and colonies within a volume of space where communication and return remain possible. Both approaches could coexist. Humanity might pursue multiple exploration strategies simultaneously, with different groups making different choices based on their values. Some would push toward the event horizon, maximizing range at the cost of connection. Others would build extended but continuous civilizations spanning hundreds or thousands of light years, prioritizing community over maximum distance. The universe accommodates all these choices equally. It provides the same physical laws to every traveler. What we choose to build, which trade-offs we accept, which destinations we prioritize, remain entirely human decisions, even when their consequences span cosmic distances. You exist in a universe that extends 46 billion light-years in every direction, containing structures so vast that light requires billions of years to traverse them. The scale exceeds not just human experience, but human cognitive capacity. We cannot truly comprehend these distances. Yet within a single lifetime, properly equipped with technologies we can imagine but have not yet built, a human being could theoretically cross significant fractions of that incomprehensible expanse. The universe has not constructed walls around humanity. It has provided highways stretching toward every horizon. Highways we have not yet learned to travel, but that physics declares open to anyone who masters the necessary velocity. The stars are not impossibly distant. They merely await the development of means to reach them. The galaxies are not forever beyond our grasp. They require only sufficient velocity and sufficient willingness to accept the temporal consequences of the journey. Within the equations governing motion, through space-time lies a promise that distances measured in millions of light-years could someday fall within the reach of a single human life. That promise exists in the mathematics of relativity, verified by a century of experiments, waiting for the engineering that would transform theoretical possibility into practical capability. The universe invites exploration. And somewhere between the 430,000 miles per hour we have achieved and the velocities where gamma exceeds millions lies a threshold where human cosmic exploration transforms from fantasy into reality. Understanding the true range of human cosmic exploration requires accepting a paradox. The distances accessible within a single lifetime depend not on physical barriers, but on choices about what makes exploration meaningful. A traveler willing to accept complete temporal disconnection from origin could theoretically reach galaxies billions of light-years distant, witnessing cosmic structures on the largest scales imaginable. A traveler prioritizing connection and return might limit exploration to nearby stars, building communities that maintain continuity across interstellar distances. Both approaches honor the same physics. Both exploit the same time dilation effects. Both work within the same constraints imposed by the speed of light and cosmic expansion. The difference lies entirely in human values, in what we consider worth sacrificing for the sake of discovery. Perhaps future humanity will pursue both paths simultaneously. Perhaps we will send one-way explorers to the most distant reaches of accessible space while building interconnected networks of colonies spanning hundreds of nearby stars. Perhaps different cultures will make different choices, with some prioritizing range and others prioritizing connection, creating diverse expressions of human cosmic exploration. The physics merely sets the stage. Time dilation provides a tool that could carry consciousness across otherwise impossible distances. Cosmic expansion sets an absolute horizon beyond which even light-speed travel cannot reach. Energy requirements impose practical constraints on what civilizations can achieve. But within these physical parameters, vast freedom exists for human choice. The question of how far a human could travel in one lifetime ultimately asks what we value most about the journey. Do we value seeing the farthest possible destinations, even if we can never return or share what we discover? Do we value maintaining connection to human civilization, even if this limits how far we can go? Do we value the journey itself, the experience of crossing cosmic distances and witnessing wonders unknown, regardless of whether anyone else ever learns what we found? Different answers produce different destinations. No answer is objectively correct. The universe accommodates all of them equally. It offers time dilation to those seeking maximum range. It offers moderate velocities to those seeking balance between distance and return. It offers pathways to billions of galaxies for those willing to abandon their era, and pathways to thousands of nearby stars for those wanting to build extended, continuous communities. From your current vantage point on this small planet, the cosmos stretches beyond comprehension in every direction. Distances measured in billions of light-years separate galaxy superclusters. Time, measured in billions of years, separates the Big Bang from the present. Quantities so large they become abstract rather than meaningful. Yet the physics you inhabit, the same physics that describes falling apples and orbiting planets, also describes how consciousness could potentially traverse these cosmic scales. The equations are clear, the effects are verified, the possibilities are real, waiting only for the engineering capability to transform potential into achievement. How far could a human actually travel in one lifetime? As far as human values permit, as far as human technology enables, as far as the cosmic event horizon allows, but not limited by the fabric of space-time itself, which provides pathways to distances that would humble the ancient gods. The distance a human could travel in one lifetime is not ultimately limited by physics. It is limited only by our imagination, our determination, and our willingness to pay the price the universe demands for passage to the stars.